Hello. In this video we are going to take a look at concavity. And so concavity means whether our function slope is increasing or decreasing. And what it actually shows up on the graph is if a function is concave up, it's going to look like a cup, meaning that our graph is going to be as we move out, it's going to be increasing at an increasing rate. Concave down looks like a frown. And so our graph is going to be slowing down. And so if we look at this first graph here, we're identifying where it's concave up and concave down, and then identifying any points of inflection. We see that we've got, this is an undefined point, but we have a point here where we see it's going down on the left, and it's increasing at a faster rate on the right. And then, of course, we have a discontinuity here, but we get that that graph is concave down to the right of 1. And then we've got a vertical asymptote there at 3, so it's going to change, but we see we've got the concave down again on the other side. And then looks like about right here, our graph is changing from that concave down to the concave up shape. And so we will see that this graph is going to be concave up. Our arrows are pointing closer together when it's concave up. If we talk about arrows that are on the top of the graph, perpendicular to the graph, and we see that when it's concave down, our arrows are spreading out. We get that frown shape. And so it's going to be concave up on the two intervals to the right of -2 until we get to x = 1, and it's also going to be concave up once we get past whatever this point over here, I'm going to say that's about 5, on to infinity. And this graph is concave down. It's going to be concave down to the left of -2 here. It's concave down to the right of 1. And it's concave down to the left of 5. And so we see that that graph is going to be concave down from -infinity -infinity until -2, and then also from 1 to 3. And it breaks at 3 because of that asymptote. 3 to 5, it's concave down on each of those intervals. So we've got concave down, I've got highlighted in yellow. Concave up, I've got highlighted in the green. And then the point of inflection is where that concavity changes. And so here we don't have we've got a discontinuity at 1. And so we don't really have a point of inflection at 1, but we do here at -2 and at 5. So we have a point of inflection when x is equal to -2, it looks like that y value is 3. And when x is equal to 5, it looks like that y value is probably about 4.5. And so those are the points where it changes. So that's looking at a graph. Now let's do an example where we are looking at the equation. And so this is going to work very similar to the way that we found the max and mins of our function when we were looking at the first derivative. The only difference is now we're going to take a second derivative and do that same basic approach. So in order to find our second derivative, we do have to find our first derivative. So here we have the function f of x equals -2x cubed plus 12x squared plus 166x minus 4. And when we take that derivative, we'll get a -6x squared plus 24x plus 166. And then we need to take the second derivative so we can find those possible inflection points, kind of like the critical points that we saw with the first derivative. We take that derivative, we're going to get negative 12x plus 24. And so there's not a real uniform term that we use for the points that we're just about to find. If it were a first derivative, we'd call them the critical points. Some people call them the critical points for the second derivative. Some people call them possible inflection points. It really doesn't matter what you call them, but we do need to find where our second derivative is either undefined or equal to 0. So we've got a polynomial here. Polynomials are never undefined. So the only possible point of inflection, the only critical value for our second derivative, is going to be when that second derivative is equal to 0. So we'll add 12x to both sides and divide by 12, and we get that x is equal to 2. And this is a polynomial, so our domain is all real numbers. So the only place where our function could change concavity is at that point at x equal 2. And so we're going to pick a test point on either side. And I'm going to pick 0 on the left and 3 on the right. And we are plugging those into our second derivative. Make sure if you're looking for concavity, you're plugging into the second derivative. So f double prime of 0, if we plug 0 into that second derivative, we're going to get negative 12 times 0 plus 24. So that's a positive number. That means it's concave up. That means that our graph is going to look like a cup to the left of 2. And then if we plug in 3, negative 12 times 3 is negative 36, plus 24 is a negative 12. Since that's a negative number, it is going to be concave down, so it's going to look like a frown. So we get that our function is concave up from negative infinity to 2, and it's concave down from 2 to infinity. And this does have a point of inflection because that point at x equal 2 is in the domain of our original function. That is a point of inflection. And so to find that y value, we're just going to plug into our original function to find the y value. And so we see that we have a point of inflection, I'm going to call it a POI, at the point where x is equal to 2. And then if we plug in 2 into that original function, we're going to get negative 2 times 2 cubed plus 12 times 2 squared plus 166 times 2 minus 4. And I get 360 for that. So remember, this is a point, and these are intervals. All right, I'll see you guys next time.